Good day, everyone. Today I'm going to speak with you about electrophilic aromatic substitution. So this is sort of a new class of mechanisms, if you will. Now, just a little bit of history with benzene. As you've been instructed, this is an aromatic structure. Okay, so when these electrons are constantly resonating about this ring structure, about an sp2 hybridized carbon cyclic structure like this, there is a lot of stability. Okay, so in order for these electrons to kind of venture outward and amend to something sort of like you saw recently with electrophilic aromatics, electrophilic addition from the prior semester. This time around, it's not quite as straightforward. Okay, so when we refer to the substitution, it actually takes place where a hydrogen originates. Okay. Now, seeing as this is such a stubborn and stable, rather, substrate to work with, you need some kind of catalyst to work with, okay, in order to generate a strong electrophile. So in other words, something that is electropositive, right? It may or may not actually have a charge, but it's certainly deficient of some kind of electronic presence. Okay, so strong electrophiles need to be generated in situ. So what that means is that standalone, they're not going to be there by themselves. They have to have something to, it's not something you can just pour out of a bottle and have it magically appear. In situ means that something needs to be made in the situation. Okay, so electrophilic aromatic substitution, it's going to be a slow step to coordinate, but then fast to remove that hydrogen. So something has to be working sort of as a base to remove that hydrogen, but that hydrogen, once the electrophile is attached, is going to be very acidic. Okay, and I'll show you why here in a minute. So you're going to see what is referred to as a sigma complex. Okay, so it's some kind of intermediate that's going to be charged. So again, like from last semester where I told you guys to sort of follow your charges, same difference is going to happen over here. Okay, so in other words, you're going to be following a positive charge throughout. All right, so we're going to go through sort of the generic mechanism that you have already in your notes. So we're just going to take a regular old benzene substrate with a hydrogen attached to it. Hydrogen's all around the ring, right? Just a naked benzene ring. So this positive electrophilic species is going to be here. And now, just like electrophilic addition, this lone pair, or sorry, not lone pair, but pi bond is going to lend its electrons. That those two electrons are going to coordinate to the electrophile. Okay, and as a result, you're going to get a positively charged species about the ring. Okay, so this electrophile is hanging on the same carbon where that hydrogen is that I've indicated from the first step. Okay, and then by having this positive charge here, it's going to pull these electrons further away from that hydrogen to make it more acidic. Okay, so what's really driving this hydrogen getting removed and these electrons popping back over is, as you would expect, aromaticity, i.e. stabilization. Okay, so now we have some base, some generic base, whatever it is, picks up that hydrogen and aromaticity is reestablished. Okay. Oops. Single-ended arrow for the next step, and then boom. In lieu of the hydrogen that was there, we now have our electrophile or electrophilic species amended to that carbon. Okay, so that's where the substitution takes place. So that's just the general mechanism. You'll see many like it that are pretty much have the same nuts and bolts. Now I referred to something what is referred to as a sigma complex. Okay, now their sigma comes from this sp3 hybridized intermediate carbon right here. Okay, so that means that these pi bonds can still shift around these 5 other carbons that you see right here. Okay, so in other words, you just flip over these pi electrons over to this next next bond here, and then you'll have a positive charge there. So just like your resonance forms, that you learned in the beginning of last semester, all of those positive charges jump to nuclei. Okay, so it'll show up here, here, and here. So it's just going to be, it's always going to be ortho or para to where the substitution's actually taking place. Okay, so earlier I discussed forming an an electrophile through the use of a catalyst. So aluminum trichloride was an effective super acid catalyst. Okay. So remember that chlorine is going to be much more electronegative than aluminum, so it's going to be pulling electron density away in 3 different directions. So that means aluminum is pretty much electron starved in this particular instance. Okay, so if you have, let's say, Cl2, whoops. Okay, so this is going to coordinate directly. This is going to be electron rich. This is going to be electron deficient. And in the out process, you're going to have aluminum. I'm not going to draw the electron pairs again, the lone pairs anyway. You have this positive charge here, okay? At least I'll do it for these anyway. Okay, so now that this is positive and now aluminum is negative, so just quick back of the envelope calculation here. Formal charge of aluminum. Aluminum is 3 electrons in valence electrons in the ground state, minus how many bounded electrons? 1, 2, 3, 4, 5, 6, 7, 8, divided by 2. No lone pairs, so that means -1. Okay? So that's where that negative charge comes from. All right, so what that means is that if this is positively charged, that means it desperately wants its electrons back. Okay, so in that event, we have aluminum trichloride or tetrachloride anion, and then we have Cl plus. Okay, so in other words, this is the electrophile that we've generated. Okay, and then aluminum, this anion that you see right here, these two are going to stabilize one another, but this is going to actually act as the base and pull off that hydrogen off the ring from the chlorination, and then you're going to get HCl as a byproduct. Okay, so I have a little bit of a story to tell you I'll finish up this mechanism real quick, and then I'll tell you a story out of that. When I was in grad school, I was having an undergrad shadow me, and he wasn't the most interested in what was going on. He was kind of more interested in the new Gorillaz album or whatever was happening at the time. And I told him to do something and to actually vent this kind of reaction, something similar to it. And, well, effectively it builds up HCl gas, which is not really something you want. Okay? Now, before I continue the story, notice here how the positive charge is getting picked up by the electron-rich species again. So we'll just put the positive charge right here. And then we have our Cl hydrogen sigma complex. Okay, so now, again, one of these chlorines is going to act as a base to pick up this particular hydrogen. Okay. And your aromaticity is reestablished. Your HCl goes, okay, as a gas. So that's what was building up pressure that he didn't relieve, staring at his new Gorillaz album or whatever. And then, poof, a bunch of aluminum trichloride, substrate that wasn't exactly this, but another aromatic species. And then HCl went all over the place. And thankfully, I was wearing goggles instead of glasses that day. Because if not, one of those little things would have gone right into my eyeball. So, if you ever want to hear about a good safety story for why you should wear goggles instead of glasses, that's the one. Okay, so there's the monochlorinated product. Sorry if the sun's in your way. Sorry if there's noise in the background. It's annoying me too, even more than it's probably annoying you. Anyway, so there you have it, a monochlorinated product. Okay, so just a quick recap: electron deficient, electron rich, goes to the electron deficient. At this point, this is electron starved. It's going to take those electrons away, making this now electron deficient. Electron rich species comes around, picks it up. It is now electron deficient, but something has come around to take a hydrogen away that is also electron deficient, because these electrons are going back up into the ring into a more stable or aromatic form. There you have it. Okay, so Friedel-Crafts kind of works the same way as what you just saw with halogenation or chlorination, as it were. But instead, you have one species that is a lot more electrophilic by itself. So this is something you haven't, you've already kind of seen on your own. But we're going to consider some other variables here. So this is why it's still kind of good to know your mechanisms and things of that nature, especially when you're thinking about stable intermediates and what have you. Because in the end, you're going to look at things in more of a synthetic focus, but you still need to sort of understand what's going on underneath the hood, so to speak. Okay, so we have this. Wow. Alkyl halide. Okay. And we have an aluminum trichloride. Catalyst. Now, once again, this is going to be electron deficient. This is going to be electron rich. So there we go. So in effect, it's going to pull this away and form a positively charged carbocation. So it almost like initiates a heterolysis, okay? Sort of like what you saw with your SN1 reactions from last semester. Okay, so that's the first step. We have our carbocation. Okay. So is this the most stable carbocation species? No. We can do better via hydride shift. So when I do hydride shifts, I have this little tilde with a H beside it to indicate that this hydrogen is shifted over to form a more stable tertiary as opposed to secondary carbocation. Okay, so this is an electron-starved species. Again, this is going to behave as a base. And then you're going to have your alkylated product. Okay? So the trick with, or the trap, if you will, with Friedel-Crafts alkylation, not acylation, because we'll get to that in a minute. The trick with Friedel-Crafts alkylation is that unless you have, let's say, a primary carbocation or primary substrate or alkyl halide, you're going to get some rearrangement, unfortunately. So this is something that's not easily, seriously not controlled. Another issue is that, and you'll see this later, that once you actually fuse this alkyl group onto the ring, that's going to be electron donating through the inductive effect. Okay, so in other words, what that's going to do is make this substrate even more reactive, so you're going to have subsequent alkylations as a result. Okay, so this next example is going to be similar. Instead of using an alkyl halide, this is what is referred to as an acid or chloride or acyl chloride. Okay, so instead of just the chloro group sort of heterolyzing or splitting off from the carbon construct of your electrophile, this C double bond O gets stabilized by the lone pair kind of reaching down in sort of a cascade of electrons unfolding. So what that actually does is preserve the octet about the oxygen, because it's still going to stay there, and also secure that that carbon to have a full octet as well. So what you're going to have is a linear intermediate. It's going to look like so, and I'm going to bring my benzene ring over to the other side too, just like it is on the left. Okay. So if this particular oxygen is starved for electrons, that means that this particular carbon is going to be extremely reactive, or activated as they call it. So those electrons are going to basically coordinate to it right away, too sweet. Here's another thing, is that once this is established, there can't be any other sort of rearrangement here. So really, this is great for a couple of reasons. One, those electrons go back up to the oxygen, so stabilizes that charge. Okay. So chlorine again from this anionic species is going to behave as a base. Take it up, reestablish aromaticity, and form HCl, and off HCl goes again. So you can almost see this sort of redundancy in these mechanisms. However, we're going to have different outcomes for each one, right? Your electrophiles are all different. The chemistry is mostly the same. Okay, but right here, if you have this CO double bond, that's going to prohibit this from further acylation. Okay, so this is what is referred to as Friedel-Crafts acylation. Okay, so what this CO double bond is an electron withdrawing group. So what it's going to do is actually slow down, or basically inactivate this ring from having any subsequent additional electrophilic aromatic substitutions. Okay, so if you want to just mono acylate this particular compound, you can do so and not have any more, or a mixture of products or anything messy like that. Furthermore, if you wanted to reduce this down to a methylene group, you could use something like Wolff-Kishner or Clemmensen reduction. Okay, we'll get into reducing agents later in the semester. Okay, so this next particular example is going to be proton NMR / IR analysis. Okay. So the first one is 22.65 on page 1143. Okay, so by using this particular aromatic substrate that has an acyl chloride group right here. Let's see, 3 carbons removed from the ring. With the use of aluminum trichloride, and then for the second step, using HCl in the presence of zinc mercury amalgam, you're going to get, for the first step, cyclization. Okay, so you're going to be forming your acyl ketone. 1, 2, 3 carbons, 1, 2, 3 carbons. Okay. So in other words, you've basically formed another 6-membered ring about that aromatic structure. Okay, now so the second step with HCl and zinc mercury amalgam, That is going to be what is referred to as a Clemmensen reduction. So this is going to be under strongly acidic conditions. Just a word of warning when we get into reductions that something that is acid labile, this is the particular type of reducing agent you'd wish to avoid. Okay, so after step 2, I'm just going to write 1 here, 2 here. You're going to reduce this down to a methylene carbon. Okay. Okay, so now you have an alkane ring, sort of. Okay, so what does the data actually say? Okay, so you have a whole bunch of, I guess, a multiplet there on the left-hand side with your NMR spectrum. They're around 7 ppm. So multiplet at 7 ppm. What's that consistent with? What's over here? So remember that these 2 hydrogens aren't here anymore, right? So you have a total of 1, 2, 3, 4, and well, sorry, more of this one. This is the intermediate. So these 4 hydrogens are all going to be roughly around the same area. Okay, so we'll just say that's 4 hydrogens. Okay. And then we have 2. So these 2 are chemically equivalent. These 2 are chemically equivalent. So we have something at about I'll just call it 2.7 ppm, and then one at 1.8 ppm. So this is going to be at 1.8 ppm. This is going to be at 2.7. Okay. So these will integrate to 4 hydrogens each. So notice how all of those integrations, in other words, that height of the blue integration sign that kind of goes over each peak is equivalent from all 3 signals. Okay, so there's a total of 3 signals. So yeah, this is to suggest that first Friedel-Crafts acylation took place, followed by a reduction. Okay, so 22.57, 22.67 rather. Okay, so that's just down a couple of examples here. It says when benzene is treated with dichloromethane in the presence of aluminum trichloride, as shown here, a product is formed whose IR, C13 NMR, and proton NMR spectrum are shown below. Draw this product and propose a mechanism for this reaction. Okay, so effectively, methylene chloride or dichloromethane is the electrophile. So if you took 2 equivalents of benzene, you would get and I haven't numbered either of these, so that just means that both of these are going to be in the same step for reacting this out. Okay. So let's look at the equivalents here. So we have a total of, looking at the bottom
of the proton NMR at the bottom of the page that's centered. You notice that at 0 ppm, that's just going to be the reference signal, so you don't have to pay any mind to that, at least in terms of integration. But if you were to look at how much integration you have relative between the signal at roughly 4 ppm and that at about 7.2 ppm, notice how that's just kind of a mess and an overlap there. You are going to get 10 hydrogens to 2, or a 5 to 1 proportion. Okay, so what is that actually doing to that methylene group right there? It's deshielding it considerably. If you have 2 phenyl rings like that directly attached to CH2, and notice how it's also a singlet there. Okay, so 2 here to your 10 that are surrounding both rings. Okay, so in other words, a 1:5 ratio. Notice how nothing is really jumping out at you with the IR. And then we have a total of how many different types of carbons here? 1, 2, 3, 4, 5. 1, 2, so this is an axis of symmetry. 1, 2, 3, another axis of symmetry. 4, 5. Okay. Also, if you look at the actual integrate or the size of the peaks, right, it's a 2 to 1 relationship as well. So that's also a giveaway. So in other words, you have effectively put this on once and then alkylated a second time, right, with another benzene in the presence of that aluminum trichloride catalyst. Okay, so in other words, you would really have 2 of these that would react out with methylene chloride. Okay, on to another transformation here. This is with adding a nitro group onto a benzene ring. So here is sort of the sluggish mechanism approach. This is not something you would typically use because in this case, this is acting as a base to remove a hydrogen. Okay, this is going to be very sluggish. Okay, so you're going to have NO3 or nitrate anion as a conjugate base. And then you're going to have this protonated nitric acid, which is going to be, as you could expect, pretty slow. And that positive charge is going to make this actually a good leaving group. And leave is what it will do. Okay. Then we have this NO2, a nitronium ion, that is, not surprisingly, going to be positively charged. So a formidable electrophile. Okay. So now, once again, we're going to form a sigma complex. Whoops. Almost didn't. Okay, and then NO2, just drawn out generically. Remember, this is going to be a zwitterion, so it's going to be partial positive negative charge. And then, let's say water in this instance. Because remember, water had to go from that previous step. It's going to behave as a base because this is going to be super acidic. Okay, so then we have our nitrated ring as our product. Like I said, this particular approach is going to be very sluggish. You would just see this as concentrated nitric acid. A faster way to go about this, instead of using concentrated nitric acid, is to use H2SO4 to work as a catalyst. And I'll show you how that works quite easily. Okay. So instead of nitric acid, you'll have sulfuric acid, which is much stronger, orders of magnitude more acidic. Okay. So it's going to give up that hydrogen more readily. So this is going to act as a base again and pluck that proton off more readily than it would just from just another nitric acid equivalent. Okay. So again, this is going to happen much faster. So in order for you to do a nitration, you would use H2SO4 to do things efficiently. If you were to heat, you're going to get polynitration. So that's what happens when they use H2SO4 and nitric acid to nitrate toluene. They'll get TNT or trinitrotoluene. So it's going to pop up ortho and para to that methyl group on toluene. So just to let you know what I'm talking about. So HNO3, H2SO4, and heat, you're going to get nitro here, nitro here, and a nitro at the bottom. Okay. So trinitrotoluene, you can't substitute at either of these sites because those nitro groups are going to be highly electron withdrawing and what is referred to as deactivating, which we'll see in the next module, submodule. Okay, so that's nitration. Okay, so the next electrophilic aromatic substitution I'm going to go over is sulfonation. So this is what is referred to as fuming sulfuric acid. So SO3 is going to look like so. Okay. So it's going to be a planar structure. Okay, so this is really going to be your electrophile. And seeing as sulfur is getting electrons tugged away from it from each of these three oxygens, it's going to be electropositive as a result. Okay. Okay, so this is going to be net neutral, negative, positive to be net neutral. Okay. And you would also have a little bit of water here that would be generated. So, or something acting as a base, right? It could be HSO4 minus. Okay. Remember, this is going to be extremely acidic. Okay. So it's going to pick up that hydrogen, and those electrons are going to cascade back into the pi system. Now, what does this do? It forms a highly electron withdrawing substituent. What it also does is it behaves as a good protective group, and it can also be a meta director. So kind of, I guess, just put that into the back burner of your mind. Now, I mentioned something about water earlier. Okay. So 2 equivalents of H2SO4 is going to yield SO3, H3O, and HSO4 minus. Okay. Like what you see here. Now, that means that there has to be some kind of proton transfer, right? So SO3 is the intermediate that's going to be reacting with your aromatic substrate, and hence forming that sulfonyl group. Okay. Now, this can be reversed if you just use dilute acid. Okay. So dilute acid meaning that it's mostly water. So what that's going to do is actually reverse things to go backwards. And you can take a look in your text to see that in reverse. And we will also take a look at problem 22.39. Okay. Okay, so 22.39 is on page 1139. Okay, so it says draw the mechanism and the major organic products. So we're just going to do A. Okay, so the first step for desulfonation, as it's referred, is one of the pi bonds comes out to coordinate to that hydronium ion, or H plus. Okay, so that water group leaves. Okay, and then the second step is when this lone pair kind of comes back and cascades and kicks this off, making it sort of a quasi-leaving group. Okay. So what goes by the wayside is SO3H plus, right? Because this is going to be positively charged, having 3 total bonds about that particular oxygen. Okay. So this is going to be a leaving group. Basically, the two are just going to sever apart. Okay, so in other words, it's a reversible process, and if you exploit Le Chatelier's principle and add some water, things can be reversed and go backwards. Okay, so the next transformation I'm going to go over with you is carboxylation. This is essentially just to form benzoic acid from benzene. But first step is to halogenate. So let's say we take Br2 and we use FeBr3. So this is going to act as a catalyst, and then we're going to get bromination. So I'm not going to draw the mechanism. You can see something analogous to it with the halogenation with, or chlorination rather, with Cl2 and aluminum trichloride. Same general mechanism. Okay, so that bromine group is there. If you use magnesium in the presence of diethyl ether, you're going to get a highly reactive species. Okay, so what that magnesium does is kind of wedge itself between that bromo group and the ring and makes a very powerful nucleophile. Okay, so this MgBr complex is going to be positively charged. This is going to be negatively charged. Okay. So that's where your powerful nucleophile is going to be. Okay. So if you have CO2 in the gas phase, it's going to come in, knock these electrons out. Then you have a carboxylate. So this is going to be an irreversible process. Okay, so next thing you would do is just acidify this, right, with a mildly mild acid, in other words. So this would be benzoic acid. The CO2 would just be in the gas phase, so you could use something like dry ice. It would sublimate out, pretty readily. Okay, so that's carboxylation. You could do that with really any type of alkyl bromide or something like that, and just wedge in magnesium, and then you would get your carboxylate just reacting out with CO2. Okay. Amination, not animation, is simply nitration followed by a reduction step. So amination, so forming an amine about an aromatic ring. Again, you would just use nitric acid and H2SO4. Okay, so there's your nitrated product. Again, you wouldn't apply heat because that would do polynitration. So if you use iron and HCl and then follow it up with a little bit of base, the reason why you would follow it up with base is that if you use HCl and you reduce this to an NH2, remember that primary amines are going to be weak bases. So in other words, from the first step, you would get something like this, right? And then NaOH would remove that proton, and then you would just have your organic product, which is going to, in this case, be what is referred to as aniline commercially. Okay, so the last transformation I'm going to go over with you is a diazonium salt intermediate, and this is going to be a great sort of precursor for other things you might want to add on to the ring. We'll say iodo groups, so things that would be otherwise sluggish through halogenation, or some OH, adding an OH group. So I had an aminated naphthalene ring. So again, to form this amino group, all you would have to do is nitrate first. So this is the most reactive carbon about naphthalene. Remember, you can't do a substitution about the bridge, and this is going to be affected by the electronics 2 away from it. So in other words, this is going to be the most reactive carbon. Treat this with NaNO2 and strong acid, so HBr, and around 0 degrees C. So it's really important that you keep this at 0 degrees C, or else it'll decompose pretty easily. And I'll show you why in a second. It's pretty pretty reactive intermediate. Okay, so N2 plus. So it's just going to be a linear compound right here, or a linear moiety, whatever you want to call it. Okay, so this is actually going to be a very good leaving group because it'll form N2 gas, which is irreversible and just goes out into the atmosphere where it's most abundant anyway, right? So you can actually find some of the variety of different resultant functionality from the the benzene diazonium ion intermediate, which is this. So this is a diazonium ion intermediate. And the mechanism is on the previous page. Again, the shift is going to be a little bit more towards synthesis as opposed to mechanism and mechanistic study. Okay, so this can also be used as a substrate for a dye. So you can see some of these sort of eye-piercing dyes that are made of what are referred to as azo dyes. And I can go over that with you during the review. But for now, let's just look at some of the different possibilities on page 1132 with this diazonium intermediate salt. So something like Br minus would stabilize this. Right. So you're wondering where that countercharge is going to stabilize. That's where it's at. Okay, so on 1132, you have the option. Notice how that Cu plus catalyst is used with, chlorine or chloro, bromo, even a cyano group to put over here. So if you wanted a nitrile in lieu of what this amino group is, you can do so with copper. Ki is used instead of copper iodide. Okay, so Ki is potassium iodide. And then you can use water as well as copper to catalyze that to put a hydroxyl group. Okay, or you could use something like H3PO2, which the name, hypophosphorus. That's going to be a monoprotic acid, and that's going to substitute this with just a hydrogen. Seems kind of counterproductive, but it's something you could do. Okay. All right. So all of that is going to be on page 1132. You can see that diazonium salt intermediate that you can react out with all those different reagents to get different functionality. So I'll just use copper cyanide, which I may or may not put on exams. Hint, hint. Okay, so that cyano group is substituting. So in other words, that negatively charged species is substituting that N2 group and kicking it off as a result. Okay, so speaking of synthesis, let's do a few synthesis problems, and we'll wrap up this particular lecture. Okay, so problem 22.53 on page 1141. So 22.53. Again, that's on page 1141. Okay, so the first reaction involves, and this is just going to be A through D. Okay, some of the other stuff I haven't introduced to you yet, so. Okay, so treating this with Br2 and FeBr3. For A, it's just going to be a brominated ring. Okay. Treating that with magnesium in the ground state, so it's metal magnesium, and then diethyl ether. Again, you're going to form your Grignard reagent. Sorry about that. Lapse of thought here. And then you're going to treat that with ethylene oxide, which is just a simple epoxide. So if you remember, this is just going to pop open easily from ring strain. And HCl and H2O. Okay, so what that's going to do is attack, kick these electrons off, and then you're going to form an alcohol. Okay, and put 2 additional carbons about that ring. Okay, so that H is coming from the acid. Okay, and PCC is an oxidizing agent, which will actually oxidize this to an aldehyde. Okay, so it'll be like this. Okay, so 2255 again, A through D. No, actually, we'll do the whole thing. Okay, so the first step is going to be a nitration. Oh, concentrated H2SO4, same difference. This is just going to happen faster. Again, don't apply heat if you don't want it polynitrated. Okay, treating that with HCl and iron, and then NaOH. It's going to form an amine. Wow, that was bad. Okay, treating this with NaNO2, HBr, around 0 degrees C. You're going to form your diazonium salt, and treating that with copper cyanide. You're going to get a cyano or benzene nitrile is your product. Okay. So I'm going to skip steps E and F and just go straight to F. So this is going to be F. Okay. And then this is going to be what is referred to as a convergent synthesis. Okay. So this is F. Right. And this is D, as it's referred. Okay, so F and D react out with one another, and then the second step, there's just some water and excess. So XS in parentheses just means excess. It's a lazy way of writing it. And then H2SO4. Okay. Now, that is going to yield a ketone. Where's the oxygen coming from? It's coming from the excess water. Okay. So one thing of note here is that cyano group is actually more reactive than you think. It'll be a formidable electrophile when it gets attacked by a formidable nucleophile like what you see right here. That water is going to actually manipulate and kick off that nitrogen. In place of it with that H2SO4, you're going to get ammonia that drives off, and then again you're just going to be left with a ketone. Okay. So that's G. So treating this with sodium borohydride. Sodium borohydride is a reducing agent in the presence of ethanol. It's going to reduce this to a secondary alcohol. Okay. So the hydrogen about the carbon actually comes from the sodium borohydride, and this proton actually comes from ethanol. Okay, so the ethanol is going to be a proton source. All right, last step. And the first one, you're going to use NaH, which is going to behave as an irreversible base because it's going to pluck this proton, right, and form H2 gas. And then you're going to have the alkoxide intermediate, which is going to be a good nucleophile. And you are going to, let me scoot this over so you can see everything. So for the second step, you're going to add bromobenzene. Okay, so in other words, this is going to be Williamson ether synthesis. So in the end, you will have this product. So I'm just going to draw pH as a shorthand for these phenyl rings. And then pH here as well. So this is a CH2 group right there. And that's going to be your final product. Okay. Nitration followed by reduction to get an amine. Treating that amine with NaNO2 and HBr is going to form a benzene diazonium ion intermediate, stabilized with Br minus. Okay. And reacting this with copper cyanide is going to give you benzene nitrile. Reacting that with a Grignard reagent, you're going to get a ketone. Again, diphenyl ketone here. This is going to be a reducing agent to reduce that ketone down to an alcohol. Deprotonating the alcohol with NaH is going to be irreversible. So using NaOH, you would have sort of a flux of anions, and therefore you would have a mixture of products, which wouldn't be good because you would just make, benzyl alcohol or something like that in addition to the ether you were attempting to make. So the second step, again, you're going to do that in two different steps. Adding that benzyl bromide, which I've used this before, it's pretty nasty. It'll make you cry. It actually made me taste like it was like this aftertaste with cherry cola that really kind of bugs me. And that was like, that feeling on steroids was awful. So anyway, you're going to form this ether. Again, Williamson ether synthesis. You saw that from last semester. Williamson ether synthesis is also covered in Chapter 10 if you're curious about that. Okay, that wraps it up. Everybody have a good one. Take it easy.